Hello, differential equations students. Welcome to part 2 of our lesson on non-homogeneous linear systems. In our last video, we used the method of undetermined coefficients to solve our system of equations. In this part of the lesson, we're going to take a look at the method of variation of parameters. So if we're going to be using the method of variation of parameters, we need to know a few things about our fundamental solution sets. So we're going to start out by thinking about the homogeneous linear first order system, y prime equals p of t times y. Now, there are three different things that we can say about solution matrices to these homogeneous systems, and those are the three things that your theorem 4.9 is going to address. The first is, let's suppose that psi is any solution matrix to that homogeneous linear first order system. Then that means that since it's a solution matrix, it satisfies the differential equation. So psi prime is going to be equal to p of t multiplied by psi. Now, if psi naught is a constant matrix and t naught is some value in between a and b, our open interval, then there's going to be some matrix psi of t where psi prime equals p of t multiplied by psi, and psi evaluated at t naught will be equal to that constant matrix psi naught. So this is just saying that we can establish an initial condition using that solution matrix. Now, here's where we start going from just a solution matrix to a fundamental solution matrix. So if it turns out that our constant matrix is invertible, then psi of t is going to be not just a solution matrix, but a fundamental matrix of that homogeneous first order system. Now, if we start with psi of t and we nail down that it's a fundamental matrix, and then we have a psi hat of t that's any solution matrix, then there's going to be some constant matrix where if we take our fundamental matrix, multiply by that constant matrix, that'll give us psi hat. Psi hat is a fundamental matrix only if the determinant of that constant matrix is non-zero. So those are three things that we can be sure of when we're dealing with solution matrices and fundamental matrices of the homogeneous first order system. And we're going to take this stuff and we're going to use it to help us go through the method of variation of parameters. All right, so variation of parameters. What I want to do is come up with a formula that I can use to come up with a particular solution using variation of parameters. And this is going to be very similar to what we did in the second order differential case. So remember what we're dealing with is we've got this non-homogeneous system of first order differential equations. So we've got y prime is equal to p of t multiplied by y plus g of t. And we're going to have an initial condition that says y of t naught is equal to some matrix y naught. And this is all happening on some open interval of t values. Now, what I'm going to do with this problem is I'm going to start out with a fundamental matrix for the homogeneous version of this particular system. So I'm going to let psi of t be a fundamental matrix for y prime is equal to p of ty. Now, Once I've got that fundamental matrix, then what I'm going to do is think about what I would need for my complementary solution. Remember, the complementary solution to our non-homogeneous system is a solution to the homogeneous version of the system. So that means that my complementary solution is going to look like y sub c of t is equal to psi of t multiplied by some arbitrary constants. So I'm going to use little column matrix C as my arbitrary constants. So those are my constants C1 and C2. So I've got my complementary solution. It's the solution to the homogeneous version of the equation. Now, the next thing I'm going to do, remember, is take that complementary solution and multiply by some unknown function u. So it's the same thing we did back in the situation where we had a single second order differential equation. It's just now, instead of u being a scalar function, u is going to be a vector function. So I'm going to look for a solution with a particular format. Y of t is equal to psi of t multiplied by u of t. So what we're going to do is we're going to take this solution and we're going to substitute this in to our system of differential equations. So I need to start out with the derivative of this thing. So I'll have the derivative of psi multiplied by u plus psi multiplied by the derivative of u, like so. And then that thing is going to be equal to p of t multiplied by psi of t multiplied by u of t. Again, doing the little substitution for y right here, plus whatever g is. So now that we've substituted, if you take a look at this thing, we see in here that psi prime plus u of t right here can be replaced, because we know that psi prime, psi was the solution of the homogeneous version of that equation. So psi prime is the same as p of t multiplied by psi. So I can write that as psi prime u of t is the same as p of t times psi of t times u of t. And now I can see that I can do a little bit of canceling, because on both sides of the equation I now have p of t times psi of t times u of t, right here and right here. So those are going to cancel each other out and leave me with a simpler equation. So now I'm left with psi times u prime is equal to g, like so. And what I want to do is I want to solve this for u prime. Now remember, psi is a fundamental matrix, which means that psi is invertible. So I'm going to multiply both sides by psi inverse. And now over here, well, psi inverse times psi is the identity, so that leaves me with u prime. So I now have that u prime of t should be equal to psi inverse of t multiplied by g of t. So now I know what form that little extra u prime should have. Now at this point, I'm going to go in here and figure out what u is, because I don't really need u prime, I need u, because I'm looking for a solution that has this particular format to it. So we're going to go in here and we're going to integrate. So that means that u of t should be the integral from some starting value, t naught, up to t of psi inverse. Now I don't want my variable to be t anymore. I want it to be something I can replace later with t and t naught. So I'm going to go in here and use a placeholder variable. So since we're already using u for the name of our vector, let's use x. So we have psi inverse of x times g of x, and then we're integrating with respect to that x right there. Then we know that, well, now we've got our little u in here. If we want to, we could even pop in here and say, well, we know that we really want this to start at 0. So if we integrate all the way from 0 to t in here, we can even come in here on the end and add on our little u naught, like so. So taking all this stuff and putting it together, what we'll end up with is y of t is equal to our complementary solution. So our psi of t times our constant matrix. Our constant matrix in this case is going to turn out to be u naught plus our particular solution. So we're going to take this little u and multiply it by psi to get our particular solution. So we'll have psi of t multiplied by the integral from t naught to t of psi inverse of x times g of x dx. So right here, that's our complementary solution. And this piece right here is our particular solution. Now let's take this, this formula and do a little bit more cleaning up. We were told at the beginning of the process that y evaluated at t naught was going to be y naught. And we also know that y evaluated at t naught should be equal to psi of t naught multiplied by u naught. And u naught, we could write as psi inverse of t naught multiplied by y naught. So these two are really the same idea, just depending on which side we want to go in and isolate. So if we take a look at our formula, we can go in here and make some replacements in that formula to get a cleaned up version. So we've got y of t is equal to, now normally I don't know what u naught is, so that's where I'm going to use this little fact that u naught is psi inverse evaluated at t naught times y naught, because I'm going to know what t naught and y naught look like. Those will be given initial conditions. So I'm going to write that first term as psi of t multiplied by psi inverse of t naught multiplied by y naught, like so. And then I'll have psi of t multiplied by my integral from t naught to t, and then we'll have our psi inverse of x, g of x, dx. So this is the formula that I'm going to use for variation of parameters. So let's take a look at a problem that we're going to solve using variation of parameters. So here we have y1 prime equals negative 2 times y1 plus 5 times y2 plus 1. And y2 prime is equal to y1 plus 2y2 plus 1. And we're told that y1 of 0 equals 3 and y2 of 0 is equal to 1. So it says use variation of parameters to solve the initial value problem. So first thing I'm going to do is rewrite this as a matrix. So I've got y prime is equal to my coefficient matrix. I've got negative 2, 5, 1, and 2. And of course we're multiplying that by our little vector y. And then our non-homogeneous term over here has the constants 1 and 1 in it. So now that I've got this thing written out in matrix form, now my job is to go and walk through the variation of parameters. So first thing I need is I need psi of t. So I need a fundamental set of solutions to the homogeneous version of this problem. So that's going to be stage 1 is find psi of t. So I'm going to start out by looking for some eigenvalues. So I'm going to take the determinant of negative 2 minus lambda, 5, 1, and 2 subtract lambda. So of course we'll have minus 2 minus lambda multiplied by 2 minus lambda, subtract 5. And now let's clean that up. We'll have lambda squared. Then we're going to have, let's see here, negative 2 lambda plus 2 lambda cancels out. And then we'll have minus 4 minus 5 is minus 9, which factors as lambda subtract 3 times lambda plus 3. And we want this determinant to equal 0. So that means for eigenvalues, we've got lambda equals 3 and lambda equals negative 3. So now that I have my eigenvalues, I need to find the eigenvectors that go with them. So let's start out with lambda is equal to 3. So we'll pop in here and we'll write negative 2 minus 3 as negative 5. And we'll write 2 subtract 3 as negative 1. And we're going to multiply this by our eigenvector. We'll call the values in there v1 and v2. And we know the result of this is supposed to be the 0 vector. So this tells us that v1 subtract v2 has to be equal to 0. So v1 and v2 are equal to each other. So I'm going to let the eigenvector that matches up with lambda equals 3 be the vector 1, 1. I also need to find an eigenvector to go with lambda equals negative 3. So we'll pop negative 3 in there for lambda. So that's going to give us 1 and 5 in the top row and 1 and 5 in the bottom row. And we're going to multiply this by our vector. And we're going to come up with the 0 vector. So this one tells us that v1 plus 5 multiplied by v2 has to be equal to 0. So that says that v1 is equal to the opposite of 5 multiplied by v2. So I'm going to come in here and in this vector, I'm going to let v2 be -1, which means that v1 will be +5, like so. So now that I have my two eigenvalues and my two eigenvectors, I can write down my complementary solution. So I would have e to the 3t multiplied by vector 1, 1, and that gets multiplied by constant 1, plus constant 2 multiplied by e to the -3t, and that has the eigenvector 5, -1. So rewriting this, what I've got is e to the 3t and e to the 3t in column 1 here. In column 2, I've got 5e to the -3t and minus e to the -3t. And then my column vector on the outside, of course, has my arbitrary constants. So remember that this vector, or excuse me, this matrix made up of these two vectors is a situation where each column has a solution in it, and this thing should give me a fundamental set of solutions. So this matrix is my matrix psi of t. And if you want to check, all you have to do very quickly is take the determinant of this and see that it's non-zero. So our main diagonal is going to give us back -1, and our minor diagonal is going to give us back 5, so the determinant is definitely not 0. It's equal to -6. So we know that, yes, that is a fundamental set of solutions. So now we've come up with psi of t is equal to this matrix that has e to the 3t and e to the 3t for the first column, and 5e to the -3t and minus e to the -3t as the second column. All right, so far we've figured out what our fundamental set looks like for the homogeneous version of our system of equations. So just to recap, we've got y prime is equal to the coefficient matrix, which has -2 and 5 in row 1, and 1 and 2 in row 2. And the non-homogeneous term is the column vector 1, 1. We've found out that psi of t has entries e to the power 3t and e to the power 3t in column 1. That was our first solution in our fundamental set. And then the second column is 5e to the -3t and negative e to the -3t, like so. And then we need our initial condition. And our initial condition was that y0 was the column vector 3, 1. They told us that y1 of 0 was equal to 3, and y2 of 0 was equal to 1. At this point, we need to figure out what comes next in our variation of parameters formula. So let's remember what our formula looked like. Our formula says that y of t will be equal to psi of t multiplied by psi inverse of t0 multiplied by y0 plus psi of t multiplied by the integral from t0 to t of psi inverse of x g of x dx. So we can see that the next thing we need to do is figure out what psi inverse looks like. So that's going to be stage 2. Find psi inverse. Well, we found out just a minute ago that the determinant of psi of t was equal to -6. So remember that to find psi inverse of t, we're going to take the reciprocal of the determinant, and then inside psi of t, we're going to reverse the order of the main diagonal and change the signs on the elements in the minor diagonal. So now all we have to do is go in here and distribute our minus 1/6 power. So psi inverse, the first element is going to be 1/6 e to the negative 3t. The second element is going to be 5/6 e to the negative 3t. In the second row, the first element is going to be 1/6. Oops, there's not a negative on that 3t. That was, yeah, we're good. Okay. Then we're going to have 1/6 e to the 3t power. And last but not least, negative 1/6 e to the 3t power. And there we go. So now we've got psi inverse of t. So we see that we're going to end up using psi inverse. We also want to know what psi inverse of t naught is, so let's go ahead and evaluate that. So psi inverse of 0, we're just going to plug 0 in for all the t's, which means all of these pieces with e to a power is just going to turn into 1, so we're going to end up with the coefficients. So we've got 1/6, 5/6, 1/6, and negative 1/6 for psi inverse of 0. So now we've got psi inverse and psi inverse of 0. We're ready to move on to the next step. So there's two pieces in here that I need to deal with. I need to deal with this first part, which is going to give me back my complementary solution, and I need to deal with the second part, which is going to give me back my particular solution. So let's start with the complementary solution piece first. So I'm going to calculate psi of t multiplied by psi inverse of t naught multiplied by y naught. So for psi of t, we've got e to the 3t and e to the 3t in column 1, and 5e to the negative 3t and minus e to the negative 3t in column 2. We're going to multiply that by psi inverse of 0, which is 1/6, and 5/6 in the top row, and 1/6 and negative 1/6 in the bottom row. And then we're going to multiply by y naught, which is the column vector 3, 1. So here we go. Remember, we multiply from left to right. So we're going to take this first and second matrices and we're going to multiply them together. So row 1, column 1 is going to give us 1/6 e to the 3t plus 5/6 e to the negative 3t. Row 1, column 2 is going to give us 5/6 e to the 3t minus 5/6 e to the negative 3t. Row 2, column 1 will give us 1/6 e to the 3t minus 1/6 e to the negative 3t. And then finally, row 2, column 2 will give us 5/6 e to the 3t power plus 1/6 e to the negative 3t power. And now we've got one more stage in our multiplication. We've got to multiply that result by the column vector 3, 1. So here we go. Row 1, column 1. So we're going to take 1/6 e to the 3t plus 5/6 e to the 3t and multiply that by 3. Doing that will reduce those denominators down to 2. So we're going to end up with 1/2 e to the 3t plus 5 halves e to the negative 3t. And then we're going to take 1 and multiply it by the second entry over here so it stays the same. So plus 5/6 e to the 3t minus 5/6 e to the negative 3t. Now we're going to do row 2, column 1 again. So multiplying this first one by 3 is going to reduce those coefficients down to 1/2. So we're going to have 1/2 e to the 3t minus 1/2 e to the negative 3t. And then multiplying that second entry by 1 doesn't change it. So plus 5/6 e to the 3t plus 1/6 e to the negative 3t. Like so. Now let's go in here and clean this up, looking for like terms. So in the top row, I've got some e to the 3t's right here, and some e to the 3t's right here. So that's going to give me 5/6 plus 1/2 is 8/6, or 4/3 e to the 3t power. And then looking at the e to the minus 3t pieces, I've got minus 5/6 and plus 5 halves. But plus 5 halves would really give me 15 over 6. So 15 and 5 is 20 over 6, or 10/3. So the entry in my top row is 4/3 e to the 3t plus 10/3 e to the negative 3t. Looking at the bottom row, for e to the 3t's, I've got a positive 1/2 here and a positive 5/6 here. So that's going to give us back again 8/6, or 4/3. So we've got 4/3 e to the 3t power. And then looking at e to the minus 3t's, right here and right here, we've got 1/6 and minus 1/2. So that's going to give us back minus 2/6, or minus 1/3. E to the negative 3t. And then we see that all these denominators are thirds. So if you like, you can pull the 1/3 out of there and say that's 1/3 times 4e to the 3t plus 10e to the negative 3t, and then 4e to the 3t minus e to the negative 3t. Either one of these is perfectly sufficient for the first half of our solution. So this is our complementary solution. Now, the next thing we need to do is deal with the integral. So now that we have the complementary solution piece, we need to find our particular solution piece, which means going in and dealing with our integral. So remember what the integral piece of this problem looks like. We start out with psi of t, and we're going to multiply psi of t by the integral from t0 to t, and underneath that integral we have psi inverse of x multiplied by g of x. So in this particular instance, we have up here at the top our psi of t, our psi inverse of t, our g of t, and our t0. So we're going to plug all this stuff in. Now that psi of t gets carried along all through the problem, and since it's sort of a pain to write and write and write over and over and over again, I'm just going to ignore it for a little while and focus on the integral. Because what we want to do is the integration first, and then once we've got the integration all finished, we'll do the multiplication with the psi of t. So on that integral, I know that t naught is equal to 0, so I'm going to go ahead and fill that in. And then I'm going to fill in psi inverse of x. Now notice that all of these entries in psi inverse are multiples of 1/6. So I'm going to go ahead and pull the 1/6 out from underneath of the integral since it's a constant multiple. And in here I'm going to write e to the minus 3x, 5e to the minus 3x, e to the positive 3x, and minus e to the positive 3x power. Since g is a constant vector, g of t and g of x look exactly the same as each other, 1, 1. We're going to integrate this with respect to x. So that 1/6 is going to come along for the ride on the outside, and I'm going to go ahead and multiply these two vectors together, or excuse me, these two matrices together to get a vector. So e to the minus 3x times 1 plus 5e to the minus 3x times 1 is going to give me e to the minus 3x power plus 5e to the minus 3x power in the top. And then in the bottom, I'm going to end up with e to the 3x power minus e to the 3x power. And now I'm going to clean that up a little bit. I've got 1/6 times the integral from 0 to t. E to the minus 3x plus 5e to the minus 3x is 6 times e to the minus 3x power. And e to the 3x power subtract e to the 3x power is 0. So now I've got a much simpler item to deal with. So the 1/6 is going to come along for the ride, and now I'm going to integrate my matrix. So when I take the integral of 6e to the minus 3x, I'm going to get minus 2 times e to the minus 3x power, so that when I differentiated this thing, the minus 3 and the minus 2 would combine and give me back my plus 6. And then down on the bottom, the integral of 0 is just some constant. I don't know what it is. I'm going to call it capital A. And then I need to evaluate this from 0 to t. So that little 1/6 is just going to come along for the ride. So plugging the t in there, I get negative 2e to the negative 3t. If I plug 0 in there, e to the 0 power is 1, so that'll be a minus 2 in the second part. So let's go ahead and put some brackets in here. And then down on the bottom part, well, plugging in 0 in for a just gives me back a. And over on the second part of plugging in t for a gives me back a. Plugging in 0 gives me also a, since it's just some constant. And then we combine these guys, and we have 1/6. And then the top row of our matrix is going to be negative 2, e to the negative 3t plus 2. And then the bottom row, a minus a, is just 0. Like so. And then let's go ahead and pull in our 1/6. So negative 2/6 is minus 1/3. So we'll have minus 1/3 e to the negative 3t plus 1/3 in the top row and 0 in the bottom row. Now this just takes care of the integration. Now we need to do some multiplication with psi of t. So psi of t, we have in the first column e to the 3t and e to the 3t, and in the second column we have 5e to the negative 3t and minus e to the negative 3t. And we're going to multiply this psi of t by the result of our integral, which we had in the top row minus 1/3 e to the minus 3t power plus 1/3, and in the bottom row 0. So when we multiply this together, we'll do row 1 times column 1. So we have e to the 3t multiplied by this negative 1/3 e to the negative 3t plus 1/3. So that's going to give us back negative 1/3. and then e to the 3t and e to the minus 3t is just a 1, plus 1/3 e to the 3t power. And then the 5e to the minus 3t gets multiplied by the 0, so it goes away. Then moving down here to the second row, we'll have e to the 3t multiplied by this top row. We get the same result back, minus 1/3 plus 1/3 e to the 3t, and then minus e to the minus 3t gets multiplied by the 0 and goes away. So there is our particular solution. That means we've got one more thing to do. We need to take our complementary solution and our particular solution and add them together. So our final solution, y of t, is going to be equal to, remember our complementary solution, we had 1/3 multiplied by 4e to the 3t power plus 10e to the negative 3t power in the top row. In the bottom row, we had 4e to the 3t power subtract e to the negative 3t power. And now we're going to add this particular part in. Again, we've got that multiple of 1/3, so we may as well pull that out. So 1/3 times, we have e to the 3t power minus 1 in the top row, and e to the 3t power minus 1 in the bottom row. And then we can actually go a little bit further now and add these matrices together. Those 1/3 we can just pull right out of there, all the way to the front. So just constant multiples. And then we can add together our two matrices. So 4e to the 3t plus another e to the 3t will give us 5e to the 3t plus 10e to the negative 3t minus 1. And then on the bottom row, we'll have 5e to the 3t minus e to the negative 3t subtract 1. And there we go. We have our solution to our initial value problem. And we're all finished.